All right, well, let's go ahead and let's get started with today's lesson on Taylor series. So right now we have questions 12 and 13 to go over from the homework. If you guys have any other specific ones, definitely let Sidney or myself know, and we'll kind of go from there. So a quick overview of Taylor series. Here is going to be our general formula that we're going to use for every single Taylor series that we have. Now, the way I like to set these up is I like to create a table where I'll have something that's like n, maybe, n, and then I will go fn of x, and then my last one will be fn of a. And here we would say, okay, a is going to be some value that we're centered at. And then I'd say, okay, if n equals 0, 1, 2, 3. And generally, if you go out 3, 4, 5 terms, you can start to see a pattern, and from there, kind of get those Taylor series. So that's the way I like to start. Now, I want to point out one very specific thing from the book that may be extremely helpful for homework, exams, anything else. If you look in chapter 11 on page 768, I'm assuming you have this in your notes as well. Hopefully you have it in your notes. If not, it's a great thing to have. This is just going to be a table of important Maclaurin and Taylor series. And it gives you the radii of convergence as well. You'll see in some of the questions I chose, and actually question 12, we're going to use this table to help us a little bit when we start to try and solve this problem, work through it. So without further ado, let's go ahead and let's go over question number 12. So here, question number 12 is a little bit, it's different because they ask kind of in a weird way a question to evaluate the indefinite integral as an infinite series. And then we're given this weird looking thing. So pretty much what we want to do is we want to pull out and figure out series that we have and how we're going to kind of change them to get them into a form where we're going to have a summation. And right away, what you can see is we have an e to the x. And in that table I just showed you, e to the x is equal to our summation from n equals 0 to infinity of x to the n over n factorial. Okay, so we're going to start with that. Now we're going to imply that e to the x minus 1 is going to be the exact thing, but now n is going to equal 1 instead of 0 because we have that minus 1. Now let's think about e to the x minus 1 over 5x. We think about that, we're going to have that's equal to summation of x to the n minus 1 all over 5n factorial. And we're going to be going from n equals 1 to infinity here. Okay. So from here, now we can start to think about our whole integral of what we have. We have this 2 times the integral of e to the x minus 1 all over 5x dx. All right. So right away, I like to say, let's just do our plus c. So we're going to have c equals c plus, and now we're going to have almost essentially this thing right here, almost. So now what we're going to have is we're going to have plus integral from n equals 1 to infinity x to the n divided by 5n times n factorial. Okay. So the reason for this is here we have x to the n minus 1. We came down to x to the n, so we must include one more 5n outside, because right now we're relating this up here to n minus 1. When related to n, we're going to have 5n times n factorial. 5 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 Okay, does that make sense? I guess another way to rewrite this would be just we have times n factorial here, and kind of maybe show that a little bit better is then now that n is going to come down and we have 5n and then times n factorial. So that factorial up here just goes to that n. And then we have a 5n because we just have an n there. So this would be our answer for that question. And now if we looked at that table, we would see that our radius of convergence is equal to infinity for e to the x. So it also will be equal to infinity for this question, because our base formula is going to be e to the x. So base formula is e to the x, our radius of convergence is infinity. We'll have the same radius of convergence even if we change it just a little bit. So yeah, so now let's think about the next one. The next one is a little bit more difficult. So number 13, and I will move it up in just a second. I'm just going to write the question down. We have evaluate the limit using series. X approaches 0 of 1 minus cosine 3x all over 1 plus 3x minus e to the 3x. Okay. So those are what my numbers are. I'm assuming you'll have something similar to that with your numbers, probably just different than 3s. Now we need to think about what we have going on in the top and the bottom. So if we think about the top, we have 1 minus cosine of 3x. So this 1 minus is going to stay the same. And now cosine of 3x, we know cosine of x, so we almost know cosine of 3x. We just have a 3x instead of an x, and it's simple. It's easy as just plugging a 3 in for your x, or a 3x in for your x to that general formula. So we're going to have 1 minus 1 over 2 factorial times, this would normally be just a x squared. We're going to have 3x squared. And then we will have a plus 1 over 4 factorial times 3. Ooh, should be a 3 times 3x. Oh, this whole thing should be squared. Sorry. 3x squared times 3x to the 4th minus, and we go on forever. Thinking about our bottom, we kind of have the same exact thing. This 1 plus 3x is just we're gonna leave that alone because we don't know any kind of a power series that we can really use. But now we have this minus e to the 3x. And again, we're thinking about the same thing. Well, let's get rid of that minus right away. We have minus, then we'll have a quantity. And then e to the x, same exact thing. Now it's e to the 3x. So we're going to have minus 1 plus 3x plus 1 over 2 factorial times 3x squared plus 1 over 3 factorial times 3x cubed plus, and yep, I'm getting off the screen again, plus all the way. Okay. And what we have from here is we're going to have limit as x approaches 0, and that's not infinity. Limit as x approaches 0 of this whole thing right there, and that's disgusting. All right, so right away, these series are going to be what's going to control this. So in a sense, we can just forget about this 1 and this 1 plus 3x in the top and bottom, because our power series are continuous functions. They're always in terms of x. So that's going to be what controls. So what I'm going to go ahead and do is I'm just going to go ahead and get rid of any of my variables that really don't have anything like 1 over 2 factorial. I'm just going to rewrite it as like this stuff here, top and bottom, because that's going to be kind of what we're controlling, what's going to be controlling. So if I rewrite it, limit x approaches 0 of 1 over 2 factorial times 3x squared minus 1 over 4 factorial times 3x to the 4th plus, we go on, divided by 1 over 2 factorial times, and I messed up my squared and my cubed again, didn't I? Times 3x quantity squared. This should be quantity squared. This should be quantity cubed, and so forth. I apologize. And this should be a minus 1/2. We need to think about that minus sign. So minus 1/2. Okay. And same exact thing with this up top. We see we distributed this negative sign, so that's how we got plus 1 over 2 factorial and so forth. So if we continue to go here, then we're going to have minus 1 over 3 factorial times 3x cubed plus 1 over 4 factorial times 4x to the 4th minus, and then we go on. And I'm moving it up. I am sorry. Okay. So from here, now this is where this gets a little bit tricky. And it's a little bit different. How do I want to explain this? Okay. That should be as x approaches 0. So if we take a look at the top and bottom, we have an x squared in every single term. So what I'm going to do is I'm going to essentially just factor out an x squared from everything. So if I rewrite this again as x approaches 0, and now you see we have x squared, we'll have this will turn into x to the 2nd, this will turn into x to the 1st, and so forth. But these x squared terms in the 1st will be gone. We also need to square both our 3's. So if we go ahead and do that, limit of 9 now, 3 squared over 2 factorial minus 3 to the 4th. I'm just going to keep it as 3 to the 4th over 4 factorial times x squared. And then we continue that out. And then here we're going to divide minus 9 over 2 factorial minus, that should be plus, shouldn't it? Nope, it's minus. Minus, we're going to have 3 cubed over 3 factorial times x, and then we would have plus, and it would continue out, or it'd be minus, and it would continue out like such. So now we're at a point where we can think about evaluating. And if we look here as x approaches 0, if we plug in 0 for these x's, we're going to be left with limit, I'm going to do this, as x approaches 0 of 9 over 2 minus 0 over negative 9 over 2 minus 0. And we can say then that that limit is going to equal negative 1. And that is how you would go about doing that limit. This question it's fairly tricky with thinking about these series and thinking about having to factor out that x squared from everything to go ahead and get to a final answer or a limit we can evaluate. So this is pretty advanced for the homework. But that's probably one of the most advanced things you'll see on the homework. So yeah, if that makes sense. Number 9, you want to do number 9, all right. We will go to number 9 next. Okay, so we have a new sheet of paper. Number 9. So this says use Maclaurin series in this table, that table I showed you earlier, to obtain the Maclaurin series for the given function. And we have f of x equals x cosine of 4x. Okay, So that given table is going to tell us that cosine of x equals -1 to the n times x to the 2n divided by 2n factorial. Okay. Then we can apply cosine of 4x will then equal, the only thing that's going to be changed again is this 4x is going to get plugged in for our x. So we do that real quick. We're going to have, and I'm going to write it right below here, equals summation, and that should be a summation too, apologize, summation of -1 to the n 4x to the 2n divided by 2n factorial. And that needs to be in parentheses like that. Okay. We can then rewrite that again as summation from n equals 0 to infinity, -1 to the n, 4 to the 2n, x to the 2n divided by 2n factorial. Okay. And now if we think about what's going to happen if we multiply this by x. So the only thing that's going to be changed if we go ahead and multiply this by x is going to be this x term here. So if we multiply by x and we have an x, so we have the same base, when we multiply, we're just going to add those powers. And we're multiplying by x to the first. So when we take this, multiply by x to the first, we're going to be left with, I'm going to write this pretty neat here compared to what I've been writing, summation of n equals 0 to infinity, -1 to the n, 4 to the 2n. I'm going to divide this now by 2n factorial. We have x to the 2n times x, so it's x to the 2n plus 1. And that right there then will be your final answer for that question. Okay, do we have any more specific ones right away? All right. If we don't have any specific ones right away, I'm going to go ahead and I'm going to kind of back up to the beginning of the homework and do one question from the beginning of the homework. It's great that you guys are so far, so it may not be extremely helpful, but I figure it might not hurt to at least go back over one of the questions from the beginning, to just kind of count it into your heads. So I chose number 2 from the homework to kind of go over. It's nothing crazy. It's just kind of, it shows you how to use the table, I suppose. So here's number 2. We have f of x equals natural log of x centered at a equals 3. So we're going to use our general formula. If I can find my general formula. We're going to use this general formula right here to go ahead and solve everything. And I kind of drew it out as a table so you can follow along that way and we'll go through it. So here we go. F of x equals natural log of x centered at a equals 3, which is equal to natural log of 3 plus n equals 1 to infinity of what? So then I went ahead and I plugged in, all right, use this table to go ahead and start looking at kind of what my variables look like. And then from there, it's simply just plugging into our table. And we're gonna have this general formula for that right here. And we're gonna have fn of 3 over n factorial times x minus 3 to the n, okay? So then this first one is just going to be natural log of 3 all over 0 factorial times x minus 3 to the 0 plus 1 over 1 factorial times 3, so 1/3 times x minus 3 to the 1 plus, once again, -1 now, -1 over 2 factorial times 3 squared times x minus 3 squared. And then just one more, let's do it, why not? We'll have plus 2 over 3 factorial times 3 to the third times x minus 3 cubed. Okay. So if we go ahead and think about what we got going on, 0 factorial is equal to 1. Anything to the 0 is equal to 1, so we have natural log of 3 to start. And then let's think about our summation. So if we go ahead and think about this to start, it's looking like we're going to have plus summation now n equals 1 to infinity because we got rid of that 0. And we start to alternate here. You can see we have a -1 and then a positive, then we'll have another negative. You can see kind of up here in this table that we'll have that. So we're going to do -1 to the n. All right. And then from there, let's think about what we got going on next. Oh, I'm sorry, this should be n plus 1. So this should be n plus 1, simply because if we think about this first term, we're positive, then we're negative, positive, negative. So it has to be n plus 1. Apologies. So then think about the next thing. We're going to have, we start to look at what we got going on here, and we go 1, 1, 2, and then you see we jump up to 6. And then if we did more, you'd see we jump even more to 24. So we're going to have something. In this case, it's going to be a factorial. It's going to be n minus 1 factorial. So if we think about this first term here, 1 minus 1 is 0. Factorial is always 1. Then we have 2 minus 1 factorial. 1 factorial is 1. 3 minus 1 is 2 factorial, which is 2. And then we go 3 factorial, which is 6, and so forth. So then let's think about our bottom. This last part, I'm just going to go ahead and write this out, x minus 3 to the n. That one's pretty self-explanatory, but let's think about our bottom now. So our bottom here, we look, we're increasing our 3 power every single time. So we're going to have 3 to the n. And then we need to think about what else we got going on here. We have 1 factorial, 2 factorial, 3 factorial. So we're simply just going to have n factorial 3 to the n. And that then is going to be our answer. So does that make sense? Okay. And then if we wanted to, we could find our radius of convergence by our limit test. I'm just going to say this. I'm not going to go through doing all of it. We would do limit as n approaches infinity of absolute value of a sub n plus 1 over a sub n. And we covered that last section. So you go ahead and add 1 to all your n's in the top and then multiply by your inverse function. So yeah. And then, so actually, taking a look at this, this is correct, but we can simplify it a little bit more if we want to. And this is kind of a good thing to go over here. We have this n minus 1 factorial divided by n factorial. And if we think about factorials work, n factorial is equal to n times n minus 1 times n minus 2 times n minus 3 times blah, 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 forever. So if we wanted to simplify this, thinking about this, we could say that this is equal to, not even approximate, it is equal to natural log of 3 plus summation n equals 1 to infinity. And now this n minus 1 is going to go away and cancel with this n factorial. And this n factorial we can write as n times n minus 1 factorial. That's how those n minus 1s will cancel. So then we're left with -1, the n plus 1. We're left with the 1 on top over n times 3 to the n, x minus 3 to the n. So that's if you want to simplify it, it's going to make taking that limit and finding your radius of convergence a little bit easier. But you don't have to simplify it. Technically, that one before that is correct as well. So, do we have any other specific questions from anyone? Do you guys want to go over another one, or kind of what are you guys feeling? I did have one other one picked out, but it happened to be number 8, which really wasn't too much different than number 9 that we just covered. So if you guys want to go over number 9 or number 8, we can go over number 8. If not, we don't need to. If you guys don't have any other questions for me, scanning the homework, that's pretty much about everything you're going to run into. 12 and 13 definitely were the tricky ones on the homework. So good ask there. Yes, if you guys don't have any other questions, you're free to go. If you have questions, feel free to put them in the chat right now, or send Sydney a private message or whatever. Go ahead and speak out. If not, that's all I got for you guys.